Alright, in this video here we're going to talk about the composition of functions. And basically what a composition of functions is when you have two separate functions and you kind of combine them together to make a new function. Right? So an example might be I have the function x plus 2, and then I have the square root function square root of x. Well, if I do the square root of x plus 2, that's a composition of functions, right? Because the x plus 2 function is now inside that square root function. That's basically what we mean by a composition of functions, is like two different functions put together, combined into one. All right, so the technical mathematical notation for all that, right? The composite function f of g, right? So the notation here, that's an f is like the name of one function, g is the name of another function, and then that symbol in the middle is like a little circle. It's not the letter O, although obviously the O is also a little circle. But it's not on the same line as the f and the g. It's like up a little bit, kind of floating in between them. And it's not like the little multiplication dot either. It's an actual open circle. And that's the mathematical notation for the composition of two functions. And we just say of when we see that. So this would be, we would say this as f of g. Right? So the composite function f of g is defined by f of g of x equals f of g of x. All right? So as we can see there, when you write it this way, like these two notations mean the same thing. Right, so f of g, again, there's two separate functions there, the f function and the g function. F of g is combining them together into a single function. Right, so f of g of x, basically the way we put that together, it's f of g of x. Right, so one function, the second one here, the g function, that function is the input into that other function, the one that's written first, the f function. Right, so when you have a composition of functions, you're taking one entire function and putting that into another function as the input to that second function. All right, so that's what we mean by composition of functions. And to hopefully make it a little more clear, using like a mapping diagram here. Right, so we have our x value, our input value. Right, so I plug that x value into the g function, and I get g of x. Right, that's the output for that first function. And actually, the first function that we plug x into is actually the second one that's listed there. Right, so when we're trying to evaluate a composition of two functions, we kind of work backwards. We start with the last function on the list and then work our way towards the first one that's on the list there. Right, so we plug x into the g function, we get g of x. Right, that's the output from that g function. We then take that g of x and then we plug that into the f function, and that gives us f of g of x. Right, so when you think about it this way in terms of this mapping diagram, right, the output for that first function then becomes the input into the next function. Right, so I take that g function, I plug in x equals 2. Right, let's say when I plug in x equals 2, I get that g of 2 is equal to 7. Right, so I take that output, that 7, and I plug 7 into my next function, that f function. I find f of 7, and that gives me f of 7, or f of g of 2, I think was the number I used before. Right, so it's almost like you're doing two functions back to back. Plug a number into the first function, get the output, take that output, plug it into the next function, that gives you the output of the composition of those two functions. Right, if you put the composition of the two functions together and you can combine them into a single function, if you just take the x value and plug it into that combination, it takes you directly to the output. Right, so that's why we use a composition of two functions, or composite functions, is because rather than doing two functions back to back, let me plug this into this function and then take the output and plug it into the next function, if I just combine them together first, I can just take that input and plug it into the composite of those two functions and just get the output in one step rather than doing it in two steps. Right, but that's basically what a composition of two functions is. Right, like I said before, we have what was the example I used? Like the function x plus 2 and then the function square root of x. Well, the x plus 2 would be like our g function, and then the square root of x would be like our f function. So f of g of x would be the square root of x plus 2, right? Taking that x plus 2, that g of x function, and plugging that into the f function, the square root. So you kind of combine the functions together that way. So hopefully that makes sense as far as what a composition of functions is. Again, it's either plugging a function into another function, or it's doing two functions back to back and using the output of the first one as the input to the second one. All right, so I'm going to erase these definitions here and then do an example where we actually put together some compositions of functions and evaluate them to see what goes on there. All right, so I'll put the example up here. We have two functions, f of x equals x squared and g of x equals x minus 3. and I want to find the composition of those functions f of g and also g of f. Right? One of the things about the composition of two functions is it's not commutative. Right? So meaning that if I switch the order, I usually get a different result. There are some cases where if I have certain functions and I do the composition two different ways, I get the same thing no matter what. But generally, that's not the case. Right? So f of g and g of f usually give us two completely different things. And so when you're doing a composition of functions, you have to be careful that you're doing them in the correct order, that you get the right answer. Because if you do them backwards, it might come out wrong. Just like if you're doing subtraction and you switch the numbers and you do it backwards, you get the wrong answer. All right. So f of x equals x squared, g of x equals x minus 3. If I want to find f of g, right, well, that's f of g of x. All right, so I'm taking the g of x function, and that's going to be my input into the f of x function. All right, and so I want to find f of x minus 3. All right, so the g of x function, g of x equals x minus 3. So where the g of x is here in the parentheses, I put x minus 3. I'm finding f of x minus 3. All right, so, well, what if I wanted to find f of 2? What would I do? Well, I would plug in 2 for x and do 2 squared, and that would equal 4, so f of 2 equals 4. All right, well, if I want to find f of x minus 3, I do the same thing. Similar thing, right? Where that x is, I put parentheses x minus 3. F of x minus 3 equals x minus 3 squared. Right? That's my function f of g. Right? I take the g function x minus 3 and I put that as the input into the f function. Remember, when you're doing the composition of functions, the second function you see here is the input into the first function. It's f of g of x. Right, so x minus 3, I go to this function, wherever that x is, I put this entire function. Right, so in place of the x, I put parentheses x minus 3, and I get x minus 3 squared. Right, so that's my composition of the functions f and g. Right, so it's the quadratic function, right, squaring something, but now I'm squaring this other function, x minus 3 squared. All right, and to do g of f, right, g of f is g of f of x. Right, so now it's switched around. Right, now the f of x function, which is x squared, is going to be the input into my g function, which is x minus 3. Right, but I approach it the same way. So it's g of f of x. F of x is x squared. So in place of the f of x here, I put x squared. And now I'm doing g of x squared. Well, the g of x function says whatever's in this parentheses, I do that thing and then minus 3. So if it's an x squared in parentheses, I do that thing, which is x squared, and then minus 3. And that's my g of f function in this case. All right, so that's how you put together a composition of two functions. Literally, one of the functions becomes the input to the other one. Wherever you have an x in this g of x function, I take this function x squared and put it in place of the x, so I get x squared minus 3. Right, when I do it the other way, when I'm doing f of g, I take the f of x function x squared, and wherever that x is, I put this function, so the x minus 3 goes in parentheses in place of the x, and that x minus 3 then gets squared. Right, one function, the complete rule for that function gets plugged in place of x in the other function. That's a composition of two functions. And remember, you have to do it in the right order. Right, the second one that you see here with this little circle notation, the second one is the input into the first one. Right? And obviously, if you do it backwards, like we did the two examples here, is the same two functions, but doing them in the reverse order, you get things that are similar, right? They both involve a something being squared, they both involve a minus 3, but these two are not the exact same function, right? Those are two different things, and so you have to make sure you put them in the right order when you're doing a composition of functions. All right, so that's putting together a composition of functions. Now, if we evaluate a composition of functions, find f of g of 5. Well, my f of g function was this one here, x minus 3 squared. So f of g of 5, well, for this f of g, this composition I made, in place of the x, I put the 5. So it's going to be 5 minus 3 squared, which is 2 squared, which equals 4. Right? 5 minus 3 is 2, and then 2 squared gives me 4. So f of g of 5 equals 4. Now, there is another way you could do that without actually putting together this composition of functions here. If I wanted to find f of g of 5, right, and let me try to squeeze it in over here. Right, so that's f of g of 5. Well, what's g of 5? Well, if I do g of 5, that's 5 minus 3. All right, so it's f of 5 minus 3, which is f of 2. All right, so I take the, and this kind of is similar to how I had it on that that mapping diagram that was up here a few minutes ago. Right, x is my input. I'm plugging it into the g function. Right, so I plug in x equals 5. 5 minus 3 gives me 2. I take that output, and then I plug that into the other function, the f function, and then 2 squared is going to give me 4. Right, so f of 2 equals 2 squared, which gives me 4, which is the same result I got over here by just using the composition of functions and plugging 5 into this. Right, and really, we did the same thing. Right, when I plugged in 5 here, first I did 5 minus 3, just like I did here, and got 2. And then I did 2 squared, which is just what I did here with f of 2, gave me 2 squared, which was 4. Right? We do the same thing. It's just, do you do it as 2 separate things, or you do it all together in one single function? Right? That's what the composition of functions is putting that 2-step process together into a single function. All right, so hopefully this is making sense as far as what compositions of functions actually are. A lot of students tend to struggle with this, don't seem to grasp the idea that it's 2 different functions combined into one. That's really what a composition is. All right, to find g of f of 7, again, there's 2 ways you could do it. The easiest way, well, I already found g of f of x was x squared minus 3. So if I plug in x equals 7, that's 7 squared minus 3, which is 49 minus 3, which equals 46. Right, if I wanted to do it the other way, g of f of 7 is g of, well, what's f of 7? F of x is x squared, so f of 7 would be 7 squared. So that's g of 49. And then g of 49, well, the g of x function says take that number and subtract 3. All right, so that gives me 49 minus 3, which also equals 46. All right, so again, either way, as long as you do it correctly, either way gives you the same answer. Generally, people find it easier to do the composition of functions first and then just plug x equals 7 into this and just do it all at once rather than doing, all right, let me plug 7 into this function and get that output and then plug that output into this function. Again, it's the same steps because here we get 49 minus 3, which is what we got there to get the answer. It's just a composition of functions is a lot more convenient. And as you move into higher and higher levels of math, you deal with compositions of functions pretty often. And they're not always labeled like this is a composition of functions, but anytime you have something being squared and then there's something in parentheses being squared, that's a composition of functions. Right? Anytime you have a square root with a bunch of stuff underneath the square root instead of just an x, that's also just a composition of functions. Right? Especially when you get into calculus and start learning how to calculate derivatives and things like that, there's different rules that you have to use when you have compositions of functions. So it's an important thing to be able to recognize, oh, this is actually 2 functions here. It's x minus 3, and it's being squared. Right? That's a composition of functions. All right. I'm going to do another video where I do a couple more examples of putting together compositions and looking at compositions of functions. So if you want some more of this stuff, you can check out that other video that I'm going to do.